Hi, everyone. I'll start with a very brief summary of what we said last time so that we can easily transition into what we want to talk this time, which is the security of blockchain. So we talked about hashes. We said that a hashing function is a function that takes data of arbitrary length, could be, for example, a blockchain transaction or a blockchain block, and produces a digest of a specific size. And we talked about one of those hashing functions that we like to use is SHA-256. Then we talked about blocks. We said that blocks are in a blockchain, the way that we are describing it is sets of transactions from one person to another. And these are grouped into different records, different blocks. And one block comes after another, and each block is pointing to the previous one. Then, in order for us to simplify a little bit the visuals, we encapsulated all this valuable information into under the word data, so that we can emphasize that what makes a blockchain is that you chain those data together with a hash to the previous block and the hash of the current block. And that hash is essentially concatenating the data with a nonce, which nonce is a number that the node that is producing the block is able to change arbitrarily, and they actually are changing it thousands of times or millions of times per second until they find a hash that makes the block valid. And that was defined as a hash that starts with a lot of zeros, and that's because it's pretty unlikely to find a hash that starts a lot of zeros. This essentially creates a decentralized lottery where a lot of different miners, a lot of different nodes are all trying different nonces. It's like playing in a lottery, trying different nonces until one of them every 10 minutes wins the lottery by finding a hash that produces a block that starts with many zeros. So then we talked about blockchains. And we said that essentially each block is chained to the previous block by making a copy, by storing a copy of the previous block's hash into the current block. That's how it is. This chaining is achieved. And we spoke about two specific things that Bitcoin is introducing. One is it is the difficulty or the difficulty target, which is a number that the higher this number is, the more zeros are required for a block to be considered valid. And the purpose of this is that if people's hashing rate increases, that means that normally miners would be able to find randomly a next block in less than 10 minutes. So what Bitcoin does is every 2016 blocks, which is roughly every 2 weeks, it computes how many minutes did it take on average for a block to be found in the past 2 weeks. And if that number was higher than 10 minutes, then it reduces the difficulty. If it's lower, it decreases the difficulty. And we talked about how difficulty currently is in the order of 20 trillions. And these are the number of zeros that we need right now, 19. We also talked about the concept of a Coinbase. So every block is coupled with a transaction that is producing new Bitcoin out of thin air, and it's giving it to whoever the miner decided to give it. And the customary here is that the miner would give it to themselves or to a wallet that they control. And in cases where we have mining pools, a lot of different miners coming together, they all agree on some central let's say wallet address of the mining pool that they all want to send. If they find the block, they send the block there, and by send the Coinbase there, and by sending it there, then they split the reward. Then we looked at the data of a specific block that was produced last week. As you can see, this has a number. It starts with several zeros. An important thing we pointed out is that we don't even know who the miner was. And today we're going to talk about how come we can trust people we don't even know handling our financial transactions and our financial assets. This is the difficulty of that block. This is the nonce that this block had. And the miners made 6.25 Bitcoin because of the Coinbase, but they also made an additional 1 Bitcoin from fee rewards. These are tips that transactions included in the when so that they can guarantee that they will take place faster than other transactions if there's congestion on the network. Two quick graphs that we looked at last week was that the Coinbase is halving every roughly 4 years. Now it started at 50 Bitcoin per block, and now we're at 6.25 Bitcoin per block. And it's going to get to zero in, what's that, about 100 years. Now, the other thing that we looked at is the total hashes that all the miners of Bitcoin are producing producing every second, and this number keeps increasing. It usually has to do with the amount of interest that miners have to do this, and also obviously it also it depends on the hardware. So in the beginning we were having just simple computers mining, and now we have very customized microchips that are specifically doing SATA56 computations all day long. And this is the difficulty, which is a graph that is basically following the hashing rate, because the higher the hashing rate, Bitcoin is increasing the difficulty so that it can stay stable at about 10 minutes per block. Okay, so this is the high level of what we did last week. And now I want to start talking about why can we trust all this stuff? And primarily, I will talk about it in the sense of the following 4 elements. So the first one is an enabling factor of technology, which is public-private key cryptography. So this is the reason why we can be sure that we and only we can authorize transactions that are coming out of our accounts. Then we're going to talk about how difficult is it to actually break the underlying crypto, the hashing functions, the public-private key cryptography, etc. And then we're going to see what Bitcoin is doing in terms of how does it recognize what is the official chain. There's a rule called the heaviest chain rule that takes care of forks. And finally, if all this fails, there is economic incentives, crypto economics, they call them, that help strengthen the security of blockchain. People have interests to actually not break stuff. But having said this, let's begin with public-private key cryptography. Right. So why is this needed? Like I said, in the previous class, we were able to just write Alice sends to Bob 3 Bitcoin. We just wrote it there in the data field of the block. But there's no guarantee that Alice is the one who is actually sending those funds over to Bob. And that's what I mean in the slide by saying, this is as good as garbage, our design, because anyone could go and change and say, okay, Alice, send me funds. And Alice can say, no, 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 I didn't. So as I said, this is cryptographic signatures is the key here. So let's talk about cryptographic signatures. In the physical world, piece of papers, a person's signature is the same everywhere. or at least it doesn't depend on the document the person is signing. It just depends on the person's signing the document. So my signature would look the same regardless of whether I'm signing this document or another document. Someone could even try to forge it or copy paste it if it's a PDF, and then pretend that I authorized a certain document. But there's an invention here that in the digital world, in the cryptographic signatures world, the signature is actually a function of the message itself. So if I am signing a contract, then my signature is specific to this contract. And let's see how this works. It works as follows. There is a concept of a secret public key, private key. I will be calling it secret key rather than private key because it starts with an S, and we have the concept of a public key which starts with a P. So I want to have different initial consonant. So we have a key pair. We have a secret key and a public key that belongs to a person or is generated by a person. And then there is the algorithm, the cryptographic signatures algorithm, which contains two functions. It contains the signing function and the verifying function. So let's look at what the signing function does. The signing function gets the private key, the secret key of the signer, and a message, and produces a signature. So the message now could be something like, I authorize this person to get X amount of Bitcoin from my account. Now, there's the other function, the verify function, gets the public key of that person, gets the message and the signature, and responds with a true or false of whether the signature is valid for this specific message. So as you can see, the secret key always stays secret with the person who is authorizing something. And the public key can be public. Anyone can know about it. The message can also be public. Like, for example, on the blockchains public, most public blockchains have completely public data so that you can see that a transaction happened or not. So it's right there. And then they also include the signatures. It's also right there. And the public key is also can be right there or claimed by the owner. The interesting thing that I was saying the other day, previous lecture about these public keys, is that only the person who has the private key can produce signatures from that from the public key of the corresponding private key. Let's look at this in practice. I like this visual open source software that allows us to see this in practice. So let's say we created a public key, a private key. Here's a private key in that was created randomly. I can click create different ones, and these are the corresponding public keys. So now I could also, in this case, as a seed, I could use a number I want. And I'm getting a public key. I'll just use a very simple private key here so that we can remember it later. And how do I sign different messages? Let's look at this. So let's say I have a message, A sends to B, 1 Bitcoin. Here's a private key. Don't worry about the fact that we're still referring to Alice as Alice. I'm just building this up for you. You will see soon it's not going to be A sending to B. But this is the sign. This is a visualization of the signing function. So sign, you get you give it a message as an argument. You give it a private key. And the result of your press sign is a message signature. Okay. The message can be public. The signature can be public. This is private key. It shouldn't be public. No one should know about it. Now we have the verify function. So if we copy this data and paste it over to the verify function, and we have the same message, we have the public key of the signer and the signature of those two. And then when we click verify, we will see that this tells us that it's green. So it is verified. Yes, it's correct. So if anyone came here and said, no, actually the message was 2 Bitcoin, I changed my mind of what I want to receive, then that doesn't verify. And this is pretty much all the magic. And if you change this back to 1 Bitcoin, it verifies. Or if you try to change the public key, it doesn't verify. Or if you try to change the signature, it doesn't verify. And pretty much anything you touch here, it's going to stop saying this is a valid signature. And because there's a lot of jargon out there, in case you hear it or read it in blogs, here are three known secure signing function algorithms: RSA signatures, that is used usually on web and SSH. There is something else called ECDSA, that's based on an algorithm that's using elliptic curves. And there is another one called ED 25519. All right. So I just said that we were just using Alice again, but there is no need actually to be using Alice and Bob as the senders and the receivers. Because then in this case, we would actually need to have a functionality of looking up what is Alice's public key so that we can validate stuff. So what we can actually do is we can use Alice's public key rather than calling her Alice. And then we can just call that public key a wallet address. It's like the username that you want to send funds to, and we're done. So then we have the concept of sending from one public key Bitcoin to another public key, and that is a complete system, and we don't need to associate it with anyone, with anything else. And plus, it makes it makes an interesting property of creating the pseudo-anonymous behavior on blockchain. So you can see how the funds transfer from one account to another, but you don't really directly know who's the owner of each account or address or public key until one of them somehow connects their activity with the real world, in which case you can start tracing back who was who. And that's how they have, over the years, researchers been able to de-anonymize a lot of historical Bitcoin transactions. But anyways, the primary motivation initially here was that to make the system simple, we don't even need to have names or usernames or other things. We can just be using the public keys as the addressing system for this, for transactions to happen. And in fact, in some blockchains, it's actually advised for people to use even a different key pair, like public-private key, for every single transaction, and let the wallet handle the fact that they have multiple key pairs. So now let's look at how this looks in our system over here. We're not looking at the block, we're looking at a specific transaction. So let's say there were 20 Bitcoin that need to be transferred from Alice to Bob. We're not using Alice anymore. We're just using Alice's public key and Bob's public key. And then we need to use Alice's private key to authorize this transaction. So let's do it. Here's the signature, the authorization of this transaction. And Bob having the transaction, the public key of Alice, which is right here, and the signature can basically claim the funds. And that's how I can show this. This is the message. This is the public key of Alice. You click verify, it's all green. If Bob were to say that, no, Alice sent me 20 Bitcoin, 21 Bitcoin instead of 20, then it wouldn't verify. And even if Bob changed anything else, it will still not verify, as I was saying. All right, so now let's look at this, how it would look all together. remember last time I was showing you these blocks here that were initially being very simple. It had like a little data field, and then they started having Alice and Bob sending stuff. So now they're a little more complex. So there is still the number of blocks, there's still a nonce, there's still a Coinbase. Now the Coinbase though is not going to a Bob or an Alice, it's going to the public key that this peer has chosen, and or this node or this miner. And there's a list of transactions, each of which is signed by the using the private key of this public key over here. And if we changed anything, it would make the block invalid. There's a concept that I can talk about later, which is for optimization reasons, the actual header of the block doesn't need to actually include all the stuff that I was showing you right here. It could include only a hash of all this stuff, and then store all this stuff in a public location somewhere else, and not as part of the core system that is maintaining the whole chain of the blocks. And this is the field right here, the Merkle root. It's a hash. It's effectively a hash of all the data of all the transactions that are held in each block. And this way, you can end up with a block that has only 80 bytes. 80 bytes, not even like the block header is only 80 bytes, whereas all the data that could be stored on a block could be up to 1 megabyte, which is 1,000,000 times bigger than 80 bytes, or 100,000 times bigger than 80 bytes. Now, what have we said so far? So far, we've said that we've shown how Bitcoin becomes an immutable blockchain, and that's because every block includes a hash of the prior block, so it's immutable. If you change anything, then you can tell. Then we've said that every block must be valid. And that to make it valid, we need to have a proper nonce such that the block's hash starts with enough zeros according to some properties and values. And what we just showed now is that also every transaction must be valid. So what makes a transaction valid is basically two things. One that we talked and one we didn't talk about. The first one is that it has a validating a correct signature by the from address of every transaction, and which proves that the owner of that address is intended to make this transaction. And the second one is that the owner who was making the transaction actually had enough funds to make this transaction. And I'm making a little bit of a leap here, saying having enough funds, because Bitcoin is not exactly following the same paradigm as accounts. It's something that is called unspent transaction outputs, which we can talk later today if we have time. But let's basically simplify this to saying, if the person's account has enough funds, then the transaction is possible. If the person's account doesn't have enough funds, then the transaction is not possible. And it's up to the miner to basically scan through the whole history of the blockchain, or usually they maintain it embedded data structures in their memory of what is a valid UTXO, or what is a valid whether the transaction is funded properly, and that makes them basically approve to keep this transaction. And the nodes have an incentive to actually make sure that every transaction they put in a block is valid, because if it's not, then when they send that block to other nodes, if they succeed in finding the right nonce, the other nodes are going to say, sorry, this block doesn't look like a valid block because it has this invalid transaction inside. So we're disregarding this. We're going to keep mining this block until we find the actual valid block. So now we talked about how public and private keys make transactions something that we can trust, but we didn't say how secure are they in a way. Can someone, are they like a password and someone can just guess that password? And if someone guessed your password, then they will have access to you. They can pretend that they are you, and they can find essentially your private key and impersonate you. Let's look at hashing functions, because signatures, signing, all these signatures essentially depend on hashing functions, because the whole signing and verifying algorithm has multiple steps, but some of these steps include hashing. So that's where a big bottleneck of cracking this whole thing would be on, like cracking a hashing function. So that's why we're talking about hashing functions, even though the bigger picture is cracking a signature. So like we said, the hashing function, data of arbitrary length, is producing a digest of a specific size, and we looked at one of those. And now I wanted to talk to you about what would it mean to crack such hashing function. It's the most obvious attack is you have a hash, you have a initial data, and then you want to say, okay, I want to change this data to something else that that actually was a question last class, and then I want to pretend that something else happened instead, and then this other something else would have the same hash. This is possible, and actually this is even more difficult than what I'm trying to describe here. An even easier problem to describe here is not this specific case, but finding any two data 1, data 2 that actually have the same hash. And we know that such collisions exist because since the resulting hash is of specific size, any message that is bigger than that size, since the space is unlimited, you can find two messages that have the same hash. We know they exist theoretically, but how difficult is it to find them? Now, the other thing that I want to define here is that a hashing function is collision resistant, or like cryptographically secure, as we say, if it is very hard for that function to find collisions. And one such function is SHA-256, what Bitcoin is using. The outputs, the SHA-256 hashes are 256 bits, which if you represent it with visual hexadecimal digits like this, it's 64 hexadecimal digits. This is an example of a hash of SHA-256. Bitcoin is actually using SHA-256 of SHA-256. So it takes the message, gets the hash, and gets the hash one more time. And Ethereum is using another thing that's called SHA-3, but despite the fact that it is newer, it doesn't make SHA-256 any less secure, as we will see right now. So now let's try to, we haven't found an algorithm as a human race so far. We haven't found an algorithm that is in a smart way cracking SHA-256. So the only way that we are able to know is the brute forcing, basically trying different hashes until we find the collision that we want. Now, how many hashes do we need to try before we find a collision? So we said it's 256 bits, and because in this case, we don't even care about finding a collision of a specific predetermined values. We only need to find any collision. In the same way that it's a similar problem is you are in a classroom right here. What is the probability that two students have exactly the same birthday? This is an easier problem than saying, what is the probability of someone else has the same birthday as me? So, so in this case, I'm just basically trying to say that even though we have 256 bits, to attack the problem here, we would need to compute 2 to the power of 128 hashes, which is less than 2 to the power of 256 hashes, which would be extremely bigger, much bigger. And because we don't talk binary in, usually we don't have a feeling about binary, I'm going to translate all the numbers to decimal. So this is about 10 to the power of 38 hashes. That's a pretty big number. It's not even nowhere near to what we were talking about, the hashing rate that was millions of tera hashes per second. So that's why I'm just going to leave it as 10 to the power of 38. And now, as we saw earlier, all Bitcoin nodes together are currently computing 140 exahashes per second. So this, I will see how many exahashes per second or hashes per year we would have. So 140 times 10 to the power of 18 times 86,000 seconds per day times 365 days per year. That gives us 10 to the power of 27 hashes per year. Okay, so at this rate, this would take 100 billion years to find one collision on SATO56. So how did I find this? 10 to the 38 divided by 10 to the 27, that's 10 to 11, which is 100 billion years. So that's how hard it is for us to find a single collision, not yet to basically say impersonate Alice. So that would be even more difficult, impersonating Alice specifically, but even finding. So we haven't found any collision on SATO56. We know they exist. If you find one, you will be extremely famous. And to put this even in perspective, because 100 billion years sounds like a lot of years, but our entire universe is about 13 billion years old. So that means that it would need to take today's miners, all the miners in the world, if they stopped mining Bitcoin and started trying to attack one hash of SATO56, it would take them 7 times the entire lifespan of our universe before they can find a hash. Whoa, that sounds pretty darn secure, right? Well, there's other potential problems that could possibly happen here. So what if we have stored our secret key on our computer in plain text and we get a virus, and that virus is looking for Bitcoin private keys, and it finds our Bitcoin secret key and it steals it, sends it to an attacker. This is not going to take 7 universe lifespans. It's going to be much simpler. That's why here, relying on the cryptography and cryptographic properties is actually pretty good, but we also need good interfaces to make sure that people are using it the right way and they're not trapping yourself into much bigger problems than what the securities and cryptography is giving you. So now let's look at the next topic, which is something, an additional point. As I said, different cryptocurrencies have, oops, it's jumping. Different cryptocurrencies, let me not open it yet. Different cryptocurrencies place emphasis in different properties. So there are three. There is an old computer science theorem that has been proven that in fault-tolerant distributed systems, you can only have 2 out of 3 properties. One of the properties is whether you have fault tolerance or not, but we need this because we're building a blockchain, so we can't give up on that. And the other 2 properties is safety and liveness. Safety essentially means whether your transactions can be reverted or not. You can have forks, whether you can have 2 parts of the distributed system that may be on an inconsistent state. So one blockchain says this transaction happened and one says it didn't happen. That's safety. And the other one is liveness, which means that the blockchain, no matter what, will keep producing blocks, or the distributed system will keep making steps in the future. So there are different cryptocurrencies that take different stances. Bitcoin emphasizes liveness. It means that even if there's a network split, or even if there is a lot of computers that all of a sudden go offline, then the blockchain will continue producing blocks. In other cryptocurrencies, they emphasize the safety, which is if there is a giant network split or some other weird thing, then the nodes are going to stop producing blocks, because there is a possibility that if they produced a block, they didn't have enough confirmations from all other nodes. There's a possibility that this block might result into a fork. So there's two schools of thought here. And now I'm going to describe how the Bitcoin is solving the situation when forks happen, since we know that in Bitcoin is violating safety. So the way this Bitcoin does it is by longest valid chain rule, or the heaviest chain. So essentially, if we have a fork, uh, for some reason, there was a block 50A that was after block 49 for some nodes, and for some other nodes, there was a 50 block, and maybe they continued mining and they found a 51 and a 52. Then when all the nodes, including the ones who decided this block down here, become aware of the entire chain, including the fork, they will all basically abandon any shorter blockchains, and they will all agree that the official blockchain is the one that is the longest. And uh, and just to be 100% clear here, it's not really the longest, it's the heaviest. And by heaviest, I mean each block has a weight. The weight is the D, that difficulty. So you intuitively, you get the difficulty, you sum up the difficulty of all the blocks, and this blockchain is heavier than this blockchain, so you take this blockchain. Because someone, what could do is it could take a really small difficulty here and produce a ton of blocks, and then the sum of all the difficulties here is actually smaller than the sum of than the difficulty over here, and it's not a sum, it's a different function, but simplifying it like that. And then it would basically try to fool everyone to follow this blockchain when they actually produced it with the smaller number of zeros in the beginning. That's why it is the heaviest, but visually we can look at it like that. So what we saw now, going back to the properties of our blockchain, we already talked about the first three. Every block includes a prior block's hash, making it immutable. Every block must be valid because the nonce should have enough zeros according to the current state of the blockchain. And every transaction must be valid because it must have a valid signature. It must be actually using funds that they exist. And what we just said is that every block should be part of the blocks of the longest chain. And this is what makes our whole blockchain. It closes the loop in a way that makes all the properties that we wanted to have in Bitcoin. Now, let's look at one more thing, economic incentives. So there's a lot of different attacks that you can do on Bitcoin. None of them is considered to be catastrophic, since Bitcoin is working, but there's solutions like mitigations for each one. But I will tell you about one that's pretty important, and how the economic incentives is fixing it. So the 51% attack. So if you somehow had a mining pool or a single entity like that managed to be able to produce 51% of or more of the hashing power of every given second of the whole collection of all miners of Bitcoin, that means that this entity would be producing 51% blocks versus everyone else would be producing 49% of the blocks. That means that this entity could always be ignoring everybody else's blocks. So if there was a block 33 and then someone found 34, and this bottom row is the one that is the attacker here. And then what the attacker could say is like, oh, you found 34, don't worry, I will keep mining 34 until I find one that is sending all the Coinbase to me instead of sending it to you. And even if the rest of the world was able for a little bit to have a longest chain, on average, because they have more hashing power, this bottom chain out here will always be slightly bigger than the one up here, making all these nodes constantly dropping their blocks, saying, never mind, actually, I'm not able, my block here or these blocks here are not part of the longest chain. This chain is longer. They will always be doing that eventually. And then this will be compounding the problem, because every time the two things become the bottom one, then the top will be starting from scratch again. This is going to cause a situation where this miner will be always not getting 51% of the rewards of Coinbase rewards of the blocks, but they will be getting 100% of the rewards. Plus, they could be always, for example, excluding someone else's transactions, doing anything they want, picking what transactions to put inside. And if you want to hear more about these various attacks, then there's a class for this, CS251. Now, what Satoshi Nakamoto said early on in his prediction about Bitcoin was that this actually could be protected if you look at the incentives of people. So having someone gain 51% of the hashing power of the whole world that is mining Bitcoin is a very expensive operation to have. So this entity has an economic incentive to help make sure that the system stays honest. The system continues producing blocks in a non-malicious way, no fraud way. And that's because if they did another way, a different way, then the world would stop trusting Bitcoin, and they would feel like, wow, Bitcoin is just right now under attack. Why would we be using Bitcoin? And then they will start selling. It will start crashing, and therefore, this would undermine this person's economic interest to participate in this whole system, because they may be getting 100% of zero versus or of something much smaller than getting the 51% that otherwise they would be getting if they were playing nice. And in fact, this was tested in practice. One of the early days, mining pool ended up becoming as big as more than 50%. And what they did is they actually started rejecting people who joined that pool so that they can go below 51%. Interestingly, that mining pool doesn't exist anymore, but or it's very, very small. So that's about Bitcoin. And there's other ways that economics can come into play. So some blockchains like Bitcoin impose economic incentives that are extrinsic, such as Coinbase and tips on the nodes to make sure that they play nice. Or the argument that we just described. But other blockchains actually opt to offer absolutely no incentives for nodes. So being a node on the system doesn't give you any tips, doesn't give you any Coinbase, nothing. So what ends up happening in these situations is that the nodes who participate have an intrinsic interest to support the ecosystem. Like who could have an intrinsic interest? Like any entity that depends on a particular blockchain. Let's say someone built a decentralized application that they want it to be running. They don't want the blockchain to crash. They want like a token that is running on top of a blockchain, or a business that's running on top of a blockchain. In the Ethereum example, Ethereum is currently using the extrinsic motivations. But if Ethereum were using intrinsic motivations and it didn't have any blockchain block rewards, then think of a big token. There is a Tether. And Tether is running on top of Ethereum, and there is $25 billion worth of Tether that are being exchanged that exist on top of Ethereum. So Tether Inc., the company that is running USDT, has a $25 billion incentive that Ethereum is running flawlessly. It's fast, so they would be putting fast computers to make it run, and it is not doing any funny business where like hacked code or weird things that would be violating the cryptographic signatures and the cryptographic properties in there. So that is another way of showing different kinds of economic motivations that people can have and still play roles as nodes with intrinsic or with extrinsic motivations. Okay, so now let's get a little more maybe philosophical. So every innovation that we had in the history was there because it filled a significant gap that existed in the world. So to give you an example, for since the beginning of humanity, we had a knowledge gap. So some people knew about something, but other people didn't. When something was happening in Europe, people living in the USA did not even know about that thing happening. And people did not even know that USA existed, for example, or Americas existed, for example. There's no USA. We're talking about thousands of years ago. And then the printing press, which is basically newspaper, completely filled that gap initially, because it was very easy to print newspapers, deliver the newspapers, the news travel. Then there was the engine that came along, which filled the power gap. Before the engine existed, the only thing we had for producing power was essentially humans and animals. And it was all manual effort. And then the engine came along and filled that gap. And all of a sudden, we were able to accelerate our development much faster, because we had those engines that had more horsepower than any human. And then there was, I want to point out the internet, which is filling a lot the distance gap, because since forever it was difficult to hold a conversation or a class over the Pacific, and I bet today in this classroom, there may be some students that are actually living in other countries right now because of COVID-19, or even in a different continent. And the internet filled this gap. And I think you can guess where I'm getting with the next one. I'm talking about trust. So what the blockchain, what gap blockchain is feeling here is the gap of having necessary trust to perform certain business transactions. So traditionally, you need to either trust the other party. You have a friend. You promise that you will give him this in exchange for that. You believe, or they believe you, that you will do what you say after they do what they say. They transfer the deed of their house, then you actually need to pay them. They trust it will happen. Or if they don't, then both of you need to trust an intermediate party. There is an escrow, and then because we both trust that escrow, that if we send the funds to that escrow company, the company is not going to take the funds and leave. And if you send your property's house, the deed of your house, to that company, they're not going to take it and run. They will instead swap it and give it back to the opposite party. We need the trust if we want to have the credit companies or the bank accounts, or they need to trust that you will actually pay your debt in the end of the day. All these things now, all of a sudden, with blockchains and with smart contracts, can be part of the code. So you don't need anymore any intermediate parties for certain things. Still in the digital world, but more and more things become digital as we speak. Okay, so that was the last thing that I wanted to specifically cover today. We are at a time, so anyone, it's 10:50, so anyone who it has another class and needs to go, you guys are welcome to leave right now. That's the end of the class, but I will stay for a few more minutes until 11 for anyone who has questions, and happy to answer those questions. My background is computer science. I did my PhD at Stanford, and then postdoc. My research interests was in fault-tolerant distributed systems. So when my first thesis was a system that was comparable to how smart contracts work on Ethereum today. So it was essentially in the same way abstracting all the complexities of maintaining the fault tolerant system underneath, and making this completely abstracted and making it easy for people to essentially write a program that's running on top of a fault-tolerant distributed system without knowing all the specifics. That's in the same way that smart contracts on Ethereum, you don't need to know how Ethereum works or how like hashes work or anything. You just need to write a program in a programming language and then upload it to the blockchain. And then after that, use it as if it was a server client application, and you don't need to know anything about that. So that was my first kind of research interest. And my second research interest is in social computing and human computer interaction, and how and crowdsourcing, and how can you help people online, especially a lot of people online, to get aligned and achieve certain goals that they have, how to better do this, and how to make the interfaces in a way that they are intuitive and reliable, and they achieve the purpose that they need to achieve. So these days I'm combining these two interests of mine into uh, looking into blockchains and how we can make them more, how we can have a mass adoption, and we can bring them to where they deserve to go. I think that every time there is a new technology that is better than the previous technology, there is a lot of parties that were the leaders or of the previous technology that are being affected. And some of them, they see that they need to adapt to continue being leaders, and others, they just ignore it. So I think what you mentioned, they need to see and adapt. I can give you an example with digital cameras. What was that, 10, 15 years ago or 20 years ago, we started seeing those digital cameras that were not that great. Still film was better than cameras because they were so highly pixelated. And there were these big camera companies, and some of them ignored the problem. They said, digital photography will never be as good as film.
Yeah.
Yeah. And they went out of business. And others, they, Canon, Nikon, they embraced it. They said, we are leaders here. We actually need to embrace the technology, start getting better and better at it. We should stay being leaders in our space. So now financial institutions and countries could potentially see this either as a threat and try to stop it or ignore it. And others may see it as a challenge or an interesting evolution. And instead of trying to stop it, they try to participate in it and promote it and make it better for everyone. The technology has proven to always come and become better and better when it needs to be. I'm not sure here how much Bitcoin is going to evolve, or it needs to evolve. Bitcoin was the first currency that essentially, over the course of the last 10 plus years, it proved to the world that digital currencies, cryptocurrencies, and blockchains, they are actually possible. And not only possible, that they can actually represent economic value. So this by itself is huge. So now, whether this is also the fact that Bitcoin was the first one and it is very simple. You see in a couple of lectures, we can pretty much describe 90% of it, and then the rest is technical implementation details. That obviously makes it a little simplistic for certain things, or for certain situations that were not predicted by Satoshi 10 plus years ago. But in the end of the day, does it really matter? What's important is that now the world knows something better, and the world will adapt, whether it is by changing the code of Bitcoin, whether it is by changing our regulations, whether it is by changing our mindsets, or whether it is by creating new and different other coins that make more sense in 2021. In the end of the day, what's important here is that there is a new technology that has significant advantages.